Q, the reaction quotient. Q is actually the exact same expression mathematically as K, the equilibrium constant. It's just that if we're not at equilibrium, we say it's Q. And it just had to be called something else because if we're not at equilibrium, we can't say, oh, it's the equilibrium constant expression. So they just called it a reaction quotient. And the reason why is because typically you have some division going on. So we're dividing, hence the name quotient. Well, what's the usefulness of this? Well, let's say that we have a container that has some butane in it and some isobutane in it. And we would like to know if this is an equilibrium mixture of the two compounds. And let's say that we have an equal amount of both. Say we have 7 atoms of butane and we have 7 atoms of isobutane. Well, are we at equilibrium or are we not? We can actually just plug these numbers into the equilibrium expression to calculate Q and see if Q equals 2.5. And if it does, we're at equilibrium. And if it doesn't, we're not. That's it. So let's try it out. This one's 7, that one's 7. So in this case, Q would equal 7 over 7 equals 1. Ooh, I guess we're not at equilibrium because 1 is not the same as 2.5. Now, we can also use this to determine which direction a reaction would move to reach equilibrium. Are we going to need to make more products, or will we need to take some of the products and make more reactants in order to get to our equilibrium constant? Well, we can use Q to determine which direction a reaction will go. We'll note here that Q is less than our equilibrium constant. And so that means that we need to make Q a bigger number to reach the equilibrium mixture. Now, how do we make a number bigger? Well, we can start transferring some of the reactants to make more products because the products is on the top of the equilibrium expression. That will make this number larger, right? So let's just say that we take 3 of the N-butanes and turn them into isobutane. So we'll say minus 3 here and plus 3 over there. And when we do that out, we should have 4 of the N-butanes still left, and we'll have 10 of the isobutanes now. And let's see if we're at equilibrium at this point. So we can recalculate Q. And in fact, Q does equal K, so we are at equilibrium now. And you'll notice that when Q is less than K, we'll need to make more products in order to reach equilibrium. And of course, if Q is equal to K, then we're at equilibrium. And then we have one more option, which would be Q is bigger than K. And in that case, we would need to make more reactants in order to get down. So I'll just write that here, and then I have an example. Q greater than K. So we would need to get rid of some of the products and convert them into reactants. So, as an example, we'll use our same system, butane and isobutane, but now instead we're going to purposely set it up so that we have too much products, and we'll see how that plays out. So, if instead we only had one N-butane molecule and we had 20 isobutane molecules, then our Q would equal 20, because 20 divided by 1 is 20, and 20 is a little bit bigger than 2.5. And so we know that we need to get rid of some of these products and make some reactants out of it. In this case, let's transfer 5 of the product molecules and make some reactants out of it. So plus 5 minus 5. So if we do that, I'll have 6 reactants and I'll have 15 products. And now Q would be 15 over 6, which is 2.5. And we're back at equilibrium now. So that's how to use Q to determine which direction a reaction will need to go. Now this example was a little bit simpler because you can use some whole numbers, and you may not have to have actually calculated it to realize that this is not at equilibrium or that's not at equilibrium. You might just kind of know it. But when we get more complicated mixtures, more complicated numbers, calculating Q can be a useful thing to determine which way a reaction will go.